before I introduce to you guys about our lecturer, Professor Pilling, I'm going to introduce myself first, okay? Why I want to do so is I want to tell you very briefly how I come to appreciate chemistry. I got my PhD from the legendary Professor Williams, Foreman Williams, and a theoretician and fluid mechanics person. So after I graduated, and then I thought everything can be described in combustion by one-step overall chemistry, okay? And then those times also Professor Lignon from Spain published a legendary paper on asymptotic structure of flames. Everything's one step, and seemed to describe things beautifully well, we think. I remember once I had a chat with, in the late 70s, with, again, another legendary, I'm mentioning all the names to you guys, CEFRC. I don't know whether you guys heard of CEFRC. He's the last student of Zeldovich, and just really outstanding person. So we two were sitting there feeling good about ourselves. He said, look, we just need one step overall chemistry to describe all the combustion phenomena. That's when I was at Northwestern. He's also visiting Northwestern. But how wrong I was. So as I grow sort of more mature in combustion and then started looking into chemistry a little bit, just for fun, and then I see, wow, it's not that simple. And maybe need 2 steps. Maybe need 3 steps going out. And then finally, I become sort of convinced it's a lot more complicated than just 1 or 2 steps. So, but then I further realized that, if you want to really do it well, you have to study chemistry, combustion chemistry, from a real master, real chemist. Okay, so that's why when I structured the summer school course, I want to make sure, right? You guys in the morning, there's combustion theory on physics and all that, and then I want to make sure the other leg of combustion is covered when I structured the summer school course. So combustion chemistry, I want to make sure it's there. So I don't know how many of you, the background is not in chemistry, chemistry. Raise your hand. How many background is not there? Okay, so you will, I hope you appreciate the importance of chemistry. So what we are so fortunate to is to have Professor Pilling here, that clearly he's one of the masters, deans, great contributors in chemical kinetics. And from the school, again, the legendary school of Leeds University, they have just throughout the years, just so wonderful. And so he has given this course 2012 and 2013. 2011 and 2013, and then I grabbed him to give the course in China, and now I'm grabbing him back to teach you guys. So let's welcome Professor Pilling.
Thank you very much, Ed. Can you hear me? Is that okay? I don't know about a master, but I can at least claim to be a chemist. So I'm, as Ed said, I'm from Leeds, which is in this little place called the United Kingdom on the edge of Europe. And it's in the north of England. And this is the little town where I live. And my house is just about here. So it's quite a beautiful place in the hills of Yorkshire, and there's a picture of a very famous outcrop of rock near this town. So I'm a physical chemist. I've always worked on chemical kinetics, and in particular I've worked on what we're going to call elementary reactions, single reactions in these multi-step processes that Ed referred to. So I think Ed may have taken you a little bit by surprise. So let me just check again. on everybody's background. How many of you would describe yourselves as engineers? So quite a lot of engineers. What about physicists? A few, one or two. Mathematicians, and finally chemists. How many chemists? So there are a few chemists. So one of the things that I'm going to try to do is to give you quite a lot of background information, because what I'd like you to do is not just to assimilate facts, but it would be good if together we could try and understand the processes that are involved in chemical kinetics, in making reactions occur at the rate at which they do. So especially today, there'll be quite a bit of background information. Okay, now, combustion involves the oxidation of a fuel. And as Ed said, although we can write an overall chemical reaction, as we can there for ethanol, this doesn't describe in a detailed way just how the reaction occurs. And instead, it involves a sequence of what we call elementary reactions or single-step reactions, many of which involve atoms and radicals. So these are highly reactive species, things like the hydroxyl radical. And because they have an odd electron, they want to become a molecule, and so they react very, very quickly with all sorts of things. And so these are species with very, very high reaction rates, and this is an area in which I'm particularly interested. So what we're going to do is we're going to examine how these rates of these elementary reactions, and we'll discuss just what we mean by them later on, how they can be measured experimentally and understood and calculated theoretically. And theory has become more and more important. Speaking as an experimentalist, the theoreticians have really begun to dominate chemical kinetics, although I'd like to claim that there is still a place for experimentalists. And how chemical mechanisms describing the overall sequence of reactions, how they can be constructed and then used to model the chemistry occurring in combustion. So this is a sort of block diagram of what might be going on. So here's chemical kinetics, laboratory experiments and theory. And what we're doing there, as we'll see, is determining what we call rate constants for chemical reactions and the mechanisms of those individual chemical reactions. And we also have a process called kinetics evaluation. One of the problems with chemical kinetics, especially in the past, has been that it's been very, very hard to get precise and accurate rate constants. And using different techniques, people have disagreed about the actual values that are involved. And there have been large uncertainties associated with the rate constants. And so evaluation of those available rate data has been an important process, and that still continues. And then using these data here, which contain the reactions, the rate constants, we can construct what's called a chemical mechanism from this kinetic database. And that chemical mechanism describes how, say, ethanol is oxidized and converted into carbon dioxide and water. That process of mechanism construction is quite complex, and we'll discuss that probably on Thursday. And this is really the bulk of what we're going to be discussing in this course. We're going to be concentrating very much on these elementary reactions and mechanism construction. But what you also need to be able to do is to evaluate the mechanisms, see how good they are, by comparing them with experimenting. We'll say a little bit about that again on Thursday, and testing them, for example, against a flow reactor or against a flame, and so on. And then these mechanisms are often absolutely huge. And so sometimes for computational processes or to enable us to understand more easily what's going on in a combustion system, you might want to reduce the mechanism and produce a mechanism with fewer reactions that reproduces the processes you're interested in accurately and well. And from that, you can generate a complex model, including fluid dynamics of any degree of complexity you want, and eventually begin to apply those to combustion applications such as engines. And so this is what we're going to be concentrating on, but we've got to remember that it fits in an overall structure. We're not just doing the chemical kinetics simply because we're interested in it. We're doing it because we want to feed into these application processes. So that's a key thing, feeding into those processes, but at the same time, one of the things that we develop is an understanding of the individual reactions and an understanding of how they interact together and produce the combustion process. And the similar approaches to the one we'll discuss for combustion are applied in atmospheric chemistry. I've spent a lot of my time working on chemical kinetics for atmospheric chemical systems, as well as for combustion. And you're using essentially the same sort of approach. The temperatures are different. And also interstellar chemistry. There's some really interesting processes go on in interstellar processes, some interesting chemical reactions. One of the particular interests is that because the pressure is so very low, and you get all sorts of interesting issues arising. So I emphasize again that issue of understanding. So this is the synopsis. We're going to talk about chemical mechanisms and chemical kinetics, and also thermodynamics, how thermodynamics are essential in terms of understanding some aspects of the chemical kinetics, but also in terms of understanding heat release from those chemical reactions. We'll discuss a little bit of quantum theory, because I'd like you to understand just where some of the issues that we're facing come from. And quantum theory is very important in terms of the calculation of these chemical reaction rates. We'll talk about statistical mechanics and electronic structure calculations. Tomorrow, we'll look at experimental methods and first of all, pulse photolysis methods, which is the area that I've worked in for longer than I care to remember. Shock tubes, which is the area that Professor Hansen works on, who was lecturing this morning. And then flow and static methods. And we'll talk about detection techniques, the way in which we can observe, especially the radical and atomic species that are so important in these chemical reactions. We'll look at theoretical methods, theory called transition state theory, which allows us to calculate chemical reaction rates, and various abstruse but important issues which are summarized there. And we'll talk about something called a master equation method, which is important for a range of reactions that are more complex than some of the simple things we'll discuss. We'll look at kinetic and thermodynamic databases and at constructing chemical mechanisms, how we go about constructing them. And then at the end, we'll look at a couple of examples. Autoignition, which is an area that I'm particularly interested in and involves relatively low temperature chemistry, and then soot formation and soot chemistry. And there we come across some really quite interesting issues because the molecules are now so very large, and there are new issues we have to worry about because of that size. Okay, so let's have a look at a chemical mechanism. So this is the hydrogen-oxygen reaction, H2 reacting with O2, and the overall reaction is set out there. And this here is a a very minimal set of reactions that are involved in hydrogen oxidation. And we'll discuss these in a little bit more detail later on today. But you notice that there are reactions involving molecules, but also particularly reactions forming and then consuming atoms and radicals. And these are the very fast steps that lead to processes such as ignition in this system. And an elementary reaction is a single-step reaction. So we have a complex reaction, which is the overall process, and then an elementary reaction, which is, say, H reacting with O2 to form OH and O. We'll slightly modify our understanding of what we mean by an elementary reaction. Some of them are a little bit more complicated than that single step there. A complex reaction such as hydrogen-oxygen is made up of several elementary reactions, and the set of elementary reactions is called the mechanism of the reaction. And clearly, you need to include all of the reactions that are going to contribute significantly to the overall process. So what do we need to know about these reactions? What quantities do we need to determine and understand? So first of all, a trivial issue it might seem, but it's not quite so simple always. What are the reactants and what are the products? Because there may be more than one set of products. So for example, hydrogen reacts with O2 and forms two radicals, OH and O, but also in the presence of something called a third body, M, it can form HO2. These are very reactive species. This, especially at lower temperatures, is quite unreactive. So the balance between those two sets of reaction products is clearly important. So how quickly do the reactions occur? Some of these reactions are in competition with one another, and so which ones are going to dominate? And the speed of these reactions, the rate of these reactions, is also going to determine many of the combustion applications, combustion attributes. And this is described in something called the rate equation, which depends on the concentrations of the species involved, and something called the rate constant. And the rate constant is the holy grail of much of chemical kinetics. You're trying to measure or calculate these rate constants because they're key attributes to a chemical mechanism. What's M? Well, M is a third body, so if you're carrying out the reaction in air, in nitrogen and oxygen, then the nitrogen and oxygen can affect the rates of the reaction simply by being there, by colliding with the species that are involved. And that gives rise to what are called pressure-dependent reactions. What's the enthalpy change of the reaction? How much heat is released or consumed when the reaction occurs? Clearly important in terms of heat release in combustion. And the ratio of the rate constants of the forward and the reverse reactions. So for example, H plus O2 going to OH plus O, and OH plus O coming back and going to H plus O2. The ratio of these rate constants, as well as C, is determined by the equilibrium constant, which in turn is determined by thermodynamics. And the equilibrium constant we can get from the Gibbs energy of reaction. So there's a clear, important interplay between chemical kinetics and thermodynamics. So let's have a look at the rates of these elementary reactions. So the rate, as we've said, is determined by the reactant concentrations and the rate coefficient, sometimes called the rate constant. The terms are used rather interchangeably. The rate coefficient K, and K depends on temperature and in some cases on pressure. We also need to clearly know what the products of the reaction, and in some cases, as we've said, that isn't always clear. So here's an example, OH reacting with methane, forming water and the methyl radical. And the rate of this reaction is determined by what's called the stoichiometry of the reaction. Is everybody aware of this term stoichiometry? you're happy about it. So we're going to use the symbol nu for this. So nu I is the stoichiometry for species I. And fortunately, I think Heinz Pitch used the same notation this morning. So we're singing from the same hymn sheet. And in this particular reaction, the stoichiometry of each of these species is 1. And so necessarily, there are clear, well-defined relationships between the rates of reaction of OH. The rate of reaction of OH is equal to the concentration of OH times the concentration of methane, the species involved as reactants, raised to the power of unity, because the stoichiometric coefficients of both of them are 1. And then the rate constant here. And that rate of reaction minus DOH by dt is going to be equal to the rate of production of water, the rate of production of methyl, and also the rate of removal of CH4, necessarily because of the stoichiometry. K depends on temperature, and this is usually expressed in terms of what's called an Arrhenius equation, after the person who invented it, and sometimes in a modified form with a t to the n term here. A is called the A factor, not a very exciting term. EA is the activation energy, and N is called the temperature exponent, and R is the gas constant. And one aim of experimental and theoretical studies of elementary reactions is to determine A, N, and EA, especially at temperatures which are important in combustion, which may sometimes be quite difficult. I've mentioned the stoichiometry there, and in the case we looked at, then the stoichiometry for each species was 1. But if we look at this, say this reaction, HO2 plus HO2, going to hydrogen peroxide plus oxygen, then the stoichiometry in this case is 2. So the rate of this reaction, so dHO2 by dt is going to be equal to minus K times HO2 squared, and we put a 2 in front of it because the reaction is removing 2 HO2s each time. That's the way, if you like, in which the rate constant for this reaction is defined by putting that 2 in there. So this is the way in which the rate coefficient is determined and the rate of reaction is determined for this reaction with a stoichiometric coefficient of 2. Now, I said the rate constant depends on temperature, but why does it depend on temperature? Well, in order to understand that, let's just have a quick look at what's called the potential energy surface for the reaction. And what's happening is that as OH approaches methane, the electrons in the system have got to rearrange. We've got to transfer an electron from one of these CH bonds here into an OH bond over here. So we're getting an electron transfer there, and that's going to require an input of energy. And so the potential energy of the system is going to rise. As we'll see, we call this term here EA the forward activation energy, and there will be, if we looked at the reaction between methyl and water, there will be a reverse activation energy there, E minus A. And the two will be related through the energy of reaction, delta RU. So as you'll see, I'm going to use this sort of terminology for the energy change occurring in the reaction with a little r in there, signifying that it's a reaction energy change. So we need the rate constant and its dependence on temperature, and this is the role of kinetics, experiment, and theory. So experiment, you're just measuring it and interpreting the results you get. Theory, what you're doing is trying to calculate this potential energy surface and then use that to determine the rate constant. We need to be able to incorporate these data in combustion models, so there's going to be mechanism development. And we need a basic understanding of the physics and chemistry. So we need an understanding of thermodynamics, kinetics, quantum mechanics, statistical mechanics. And if you want, if these are areas that you feel uncertain about, then there are quite a lot of good physical chemistry textbooks around, and I would recommend this one, this one by Atkins and DePaul, simply called Physical Chemistry, in its umpteenth edition. But you'll find a discussion of all of these things there explained really very clearly by this man, Peter Atkins. Note that we use the word mechanism in two different ways. We can talk about it, we can use it to describe the way in which an elementary reaction occurs. So the mechanism of an elementary reaction, the way in which the reaction gets over this energy barrier here. Or we can use it to describe the whole system of reactions, the chemical mechanism for a combustion system. So some basic definitions in chemical kinetics: the order of reaction is equal to the exponent of the reactant concentration in the rate equation. For an elementary reaction, this is equal to the stoichiometric number nu I. I didn't put that in the notes, so you might want to insert that little nu I there. So we're defining the stoichiometry for the reactants in the rate equation. So O plus H2 going to H plus O2. The rate is K times O times H2. The order with respect to O is 1. The order with respect to H2 is 1. And the overall order is 2. Here's another reaction which we'll discuss in some detail. Two CH3s coming together to form ethane, and the rate there, as we found with the HO2 reaction, is K times CH3 squared, and we will put a 2 in there if we were talking about the loss of methyl, but there'd only be a 1 if we're talking about the formation of ethane. So stoichiometry is really very important in all of these things. Just let's say something about the units of the rate constant. So the rate constant, its units depend upon whether it's first order. So a first order reaction would be something like ethane going to 2 methyl radicals. The opposite, the reverse of that reaction over there. And you can work out what these units can be just by looking at the rate equation. It's pretty obvious what they have to be. And in this case, the rate constant has units of seconds to the minus 1. In the case of a second order reaction, so for example, what do we put up there? O plus H2. Then the rate constant has units of centimeters cubed per molecule per second. And here you need to be a little bit careful because different people use different bases for these things. I tend to work in molecular units, but a lot of combustion people work in molar units. And so this rate constant could also be in terms of centimeters cubed per mole per second. So you need to look carefully at the tabulations of the rate constants to understand what sets of units are being used. And then something called the molecularity of a reaction. And the molecularity refers to the number of species involved in the transition state. The transition state was that location at the top of the energy barrier that we saw there. So how many species are involved in that transition state? And in the case of OH plus methane, it's two species come together, OH and CH4 come together, and so it's called a bimolecular reaction. And if there's just one in the case of ethane going to two methyls, then that's a unimolecular reaction. And it's important to distinguish between the molecularity and the order of the reaction. The two are related, but they refer to very different things. Okay, you're all very quiet. Does anybody have any burning issues that they'd like to raise? Yeah.
On the previous board, where we had written the reaction and said that the rate is equal to 2 times the rate constant times the concentration, where did that 2 come from?
Yeah, okay. So here. Yeah, it arises because let me write down so that's the rate of removal of the reactant. Let's look at the rate of formation of the product, and that's going to be plus K times HO2 squared. Necessarily, because of the stoichiometry, one rate is going to be twice the other.
So the rates are in that ratio, but the rate itself, shouldn't that be just negative the rate constant times the square of the concentration?
No, that's simply the definition that we use. We could ignore it, just make it 1, but in that case, we'd have to put a half in here. Okay, the rate of forming H2O2 has to be a half the rate at which we're removing HO2. So the convention is simply a convention that we put that 2 in. Is that okay?
Thank you.
Any other issues? Do yell out. I may change that invitation if we finish up not getting anywhere very fast. But in principle, if there is something isn't clear, then do yell out. But what I would propose to do is these lectures are an hour long, and so I'll try and break them for questions halfway through. So you can say something.
About molecularity, do we look at the reactants only to decide if it's bimolecular or unimolecular?
Yes.
So we don't look at the products?
No, we don't look at the products because they could be different. So if we take two methyl radicals reacting together to form ethane, then there are two species involved in the transition state. But coming back again, there's only one. So it's bimolecular in one direction and unimolecular in the other. And there isn't a conflict there, in fact. But I think that's a good question. Yeah.
So would there be a reaction where the order of the reaction is not the same as the molecularity? Like a second order reaction will also have a bimolecular molecularity?
Yes. As we'll see, let me give you an important example of that. So if we look at CH3 plus CH3, then that's a bimolecular reaction. But what happens is that as they come together, these two species, they form a highly energized ethane molecule, which can just fall apart unless something happens to it. And what happens, so it would just come back again. And what happens to it is that it collides with this species M, this third body, nitrogen, oxygen, say, and that stabilizes it. I'll go through this later on today, but what we find is that at high pressure, this reaction is second order, but at low pressure, it's actually third order, because the concentration of M becomes important. And so that differs from the molecularity, and it also changes as the reaction, as the pressure changes. Okay?
Maybe I missed something. So for the K constant for second order, why the centimeter will appear, but for the first order there's no.
Yeah. So if we look at, for a first order reaction, say, supposing this is the concentration of our species, then that's the rate equation. Is that okay? And so what we've got here is molecules per centimeter cubed. Over here, we've got molecules per centimeter cubed per second. Let's do this properly. Molecules per centimeter cubed per second. Over here, there we've got molecules per centimeter cubed. And so this has to have units of seconds to the minus 1. All right. Whereas if this would be Ka squared, then you get a concentration term coming in. Okay, so that's why when you look down, and I'm sure everybody has looked down tables of chemical reactions occurring in a chemical mechanism, that's why it's important to look at the top and see what the units are of these various things. So there'll be first order or there'll be second order, by and large. Right, let's move on. Okay, everybody here also goes to Heinz Spitz's lectures in the morning. Is that correct? So Heinz talked about thermodynamics this morning and talked about equilibrium constants. I apologize if our notation differs slightly, but this slide emphasizes the important relationship between forward and reverse rate coefficients and the equilibrium constant. So that's a definition of an equilibrium constant in terms of what are called activities. And activities are pressure over standard pressure for ideal systems or concentration over standard concentration. So the equilibrium constant is dimensionless. The thermodynamic equilibrium constant is dimensionless. But we use other equilibrium constants because often they're more useful. And in particular, we're going to use this equilibrium constant in terms of concentrations, which is defined in terms of the concentrations of the products raised to their stoichiometric coefficient divided by those of the reactants, again raised to the stoichiometric coefficients. And these will have dimensions if the sum of the stoichiometric coefficients is different for the reactants and products. So again, you've got to be careful about the dimensions. At equilibrium, the forward rate and the reverse rate are equal. And the ratio of them establishes the equilibrium concentrations and therefore is related to the equilibrium constant. And so the equilibrium constant is simply equal to the ratio of the rate coefficients for the forward and the reverse reactions. And in combustion, that's an absolutely key relationship. Especially, I mean, if you're using something like Chemkin, then you simply put in reversible reactions, and with the thermodynamic database, Chemkin will calculate the rate constant for the reverse reaction using that thermodynamic database. So that relationship is key and central to combustion chemistry. Okay, a tiny little bit about entropy. Did Heinz get as far as thermodynamics this morning? So did he discuss the first and second laws of thermodynamics with you? Okay, so this is a very, very quick run through. notation is related but slightly different. These are the whole system quantities. The energy being related to the heat absorbed by the system and the work done on the system, and the enthalpy being related to U plus PV. And this is the first law of thermodynamics, which says that the energy U of an isolated system is constant. So you can't create energy out of nothing. The second law of thermodynamics, a statement of it, is that no process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. So we can't have a heat reservoir and simply take the energy out of it and convert it totally into work. We've got to transfer it to a lower temperature reservoir and use the difference to convert it to work. And from a notational point of view, from a mathematical point of view, that allows us to define the entropy, and the entropy is given by, is greater than or equal to the change in the heat absorbed divided by the temperature. It's greater than it for an irreversible system. It's equal to it for a reversible system. And then finally, the entropy of all perfectly crystalline substances at 0 Kelvin is 0. So S is 0 when T is equal to 0. There is a statement of these three laws of thermodynamics which is quite pithy. It says the first law of thermodynamics says you can't get something for nothing, you can only break even. The second one says that you can only break even at 0 Kelvin. Because only if your receiving heat bath is at 0 Kelvin can you convert all of the heat energy into work. So you can only break even at 0 Kelvin. And the last one says you can't get to 0 Kelvin. So basically we're screwed. Oops. Okay, Gibbs energy. On some of the slides, I've added a little bit extra. And if I've added a little bit extra, I've added a new slide, then I've put one of these little golden stars on it. You will, all of this lot will go on the web at the end. So you will be able to access it through the web on the end. So if you are so turned on by what lies behind this little golden star, then you'll have to wait until the stuff goes up on the web. Okay, so Gibbs energy, G is equal to H minus Ts. And at constant temperature, the change in Gibbs energy, delta G, is given by delta G is equal to delta H minus T delta S. And equilibrium, as you discussed with Heinz this morning, equilibrium occurs at minimum G under conditions of constant T and P. Key thing there is this interaction between enthalpy and entropy. And that's why the equation is formulated in the way that it is. Equilibrium occurs at minimum G, and from an energetic point of view, we want to go to the minimum energy. And so that's why delta G is directly proportional to delta H. But the other driving force is the increase in entropy. The direction of spontaneity is associated, other things being equal, with an increasing entropy. And so an increasing entropy is going to decrease delta G because of that minus sign there. So equilibrium is determined by these two important driving forces. And then as far as the equilibrium constant is concerned, delta G standard, the Gibbs energy change for a reaction under standard conditions, is equal to minus RT log K. And that's the thermodynamic equilibrium constant that is dimensionless that we discussed a couple of slides ago. So the equilibrium constant K can be calculated from tabulated or calculated values of standard enthalpy. And I'm sure a lot of you have used thermodynamic databases for a variety purposes, but this is one of the potential purposes. They're used to calculate, usage to calculate equilibrium constants via the enthalpy change and the entropy change. And later in this set of lectures today, we'll discuss how thermodynamic quantities can be calculated using a process called statistical mechanics, using the properties of the molecules and the properties of the energy levels of the molecules. And in a later lecture, we'll discuss tabulations of thermodynamic data, which have been revolutionized over the last 10 or 15 years. Final thing about heat relations is heat capacity. Again, discussed with Heinz this morning. The tabulations of enthalpies and entropies are usually at 298 K, but we want to use them at other temperatures. And so we have to use the relationship between the enthalpy and the heat capacity. The heat capacity is being defined in this way, Cp being at constant pressure, Cv at constant volume, and their relationship to an ideal gas is via the gas constant R. And then Kirchhoff's laws allow us to calculate a reaction enthalpy at at one temperature in terms of the reaction enthalpy at another, using the heat capacity changes in the reaction. And so we can easily go from 298 K up to whatever temperature we need, provided we have the data for these heat capacities here. Okay. Let's now have a look at energy quantization. This, I mean, we could just ignore this, but it's there and it's important, and I think it's quite a good idea if you understand roughly what it's all about, where the quantization comes from. I'm sure you have you've all done something on this, but what we're going to do is we're going to summarize it all very quickly and understand where it all comes from. So using StatMech, we can calculate energies and entropies of molecules, but this requires us to understand the quantization of their different forms of energy, their electronic energy, their vibrational energy, their rotational energy, their translational energy. The occurrence of the energy levels and their spacing is a consequence of the wave properties of matter. And atomic and molecular particles, the fact that atomic and molecular particles behave as both particles and waves. So the electron is a particle. It can collide with other species. It can transfer momentum in collisions. But it's also a wave. It also has wave-type properties because you can diffract electrons. So you can diffract electrons in exactly the same way as you can diffract light. Well, an equivalent way to which you can diffract light. And so the next few slides outline the basis of quantization and of the use of statistical mechanics. So this is quantum mechanics in 6 slides. So vast tomes have been written on this subject, but we're going to cover it in 6 slides. So first is an important relationship, which was one of the first realizations of what was going on, is the de Broglie relationship. And this says that the momentum of a particle is equal to h over its wavelength, and h is Planck's constant, which is 6.626 times 10 to the minus 34 joules seconds. So just let's do a quick calculation. So supposing we take a massive particle of, say, 100 kilograms, so a largish person, and we'll allow them to proceed with a speed of something like 2 meters a second. And we can work out lambda, because lambda is going to be equal to h over p, which is going to be of the order of 6 times 10 to the minus 34 over 200. So that tells us that the wavelength is of the order of 3 times 10 to the minus 36 meters, which isn't a lot. So we have, if you like, wave-type properties, but those, our wavelengths are so very, very small that they're immaterial, and we behave totally classically. So classical mechanics is entirely appropriate as far as we're concerned. But let's now have a look at an electron. So the mass of an electron, let me get this right, is seem to have written it down, is around about 10 to the minus 34. The mass is about 10 to the minus 34 kilograms. And let's allow this to move at a speed of about 2 times 10 to the 6 meters per second. And so in this case, lambda is going to be of the order of 6 times 10 to the minus 34 divided by 2 times 10 to the minus, that should be 31. 2 times 10 to the minus 24. Okay, so I'm sorry about that. I didn't write it down, but the mass is about 10 to the minus 31 kilograms. And so the wavelength now is of the order of 10 to the minus 10 meters, which is, 3 times 10 to the minus 10 meters, which is about 0.3 nanometers, which is about 3 angstroms. And so that's very much the dimensions of molecular systems. So because of its small mass, and importantly, because of the magnitude of Planck's constant, electrons show wave-type properties. We don't show them, electrons do. Okay, so that's the first important statement about this quantum mechanics issue. The next is something called the Schrödinger equation. And the Schrödinger equation was basically an invention. Schrödinger wanted to develop an equation which would show wave-type properties for particles. So it's a hypothesis, if you like. This is for one dimension. There is a time-dependent Schrödinger equation, but we're just looking at the time-independent one for one dimension. And it includes something called a kinetic energy operator here, which is a second differential with respect to the distance x, Planck's constant, and the mass of the particle. And the potential energy of the system, and something called a wave function here. So this is an operator operating on this wave function, and it generates the energy of the system multiplied by the wave function. And this thing here is called the Hamiltonian. So another way of writing this is h psi is equal to e psi. And those of you who are versed in classical mechanics will know that the Hamiltonian in classical mechanics is the kinetic energy plus the potential energy. So this is very much the equivalent of a classical mechanical equation, but replacing the kinetic energy with this operator here. And we'll see what the consequences of that are. And then the wave function, psi. So what happens is, in order for things to behave properly, you have to give this wave function various properties. It's got to be continuous slope, single-valued, finite everywhere. It goes to 0 as x goes to infinity, and psi squared is the particle probability density. What we'll find is that we can work out the probability of a particle being in a particular position from a knowledge of psi squared. An important consequence of that is that if we integrate that over all space, then that must be unity because the particle must be somewhere. So that's called a normalization property for this wave function. Okay, so just let's have a look at a particle in a one-dimensional box and see how quantization naturally evolves from the system using either the de Broglie relationship or the Schrödinger equation. So what we've got is a particle of mass m sitting in a box. The size of the box is L, and the sides of the potential energy is 0 inside the box and infinity outside the box. So basically, the particle can't get out of the box. It's got to sit in there. Psi must be 0 outside the box and must be 0 at x is equal to 0 and L. We can use the de Broglie relationship to say, well, okay, the wavelength of psi depends upon the momentum and therefore on the kinetic and total energy. Therefore, on the kinetic, which is the total energy. V is equal to 0 inside the box. And so we can see that we're going to have wavelengths which have to be 0, wave functions that have to be 0 here and here. And so we can get a series of sine functions. And these functions will have different, these wave functions will have different energies because the momentum depends upon the wavelength. So the shorter the wavelength, the bigger the momentum. Alternatively, what we can do is we can solve the Schrödinger equation. So here's the solution of the Schrödinger equation. So we can remove the potential energy. It's 0 everywhere inside the box. So we've got minus h squared, 8 pi squared m. Then the second derivative of psi is equal to e psi. And this is, I mean, you must have come across a differential equation of this like this many times. What's happening is you take the second derivative of this system, it regenerates the same quantity with this, allowing for this constant here with a minus sign. So it could be a e to the ikx, or in this case, it could simply be a sine function. We have a constant k within the sine function, but that constant k we can determine because the wave function has got to be 0 here and here, and so k has got to be n pi x over L. So having got this wave function, what we can do is we can differentiate it twice, and from that we can determine the energy E. And the E is going to be equal to k squared h squared over 8 pi squared m, or n squared h squared over 8ml squared. So what this is telling us is we've got a set of energies which depend upon this constant m, or this integer n, which is the quantum number, and that can take values 1, 2, 3, 4, all the way up to infinity. And the constant A is then determined from the normalization probability. Okay, just 2 minutes and then we'll go for a break. And yeah, so that's determined from the normalization probability. And so here are the wave functions for the particle inside the box. The 0 at the edges of the box, wavelength decreases as the energy increases, de Broglie. 0 kinetic energy is not allowed. If we made the wave function 0 here and here, and we gave it an infinite wavelength, then it would be 0 everywhere. So we can't have energy equal to 0. We get something called the 0-point energy, and it comes naturally out of the solution of the Schrödinger equation. So 0 kinetic energy is not allowed, and there's a so-called 0-point energy. Note the form of the energy levels. Energy is quantized and described by a quantum number n, which can take the values 1, 2, 3, 4, but not 0. And note the operation of something called a correspondence principle. If we go to very, very high values of n, what's going to happen is that we're going to get a wave function that looks something like this, oscillating very rapidly as we go across the box. And the probability of finding the particle across the box is going to be fairly even. So it could be anywhere with equal probability within the box. But that's very different when we come down here, because the most probable position for the particle in this energy level is sitting in the middle of the box. So quite different behavior from what we would expect classically. Okay, we'll take those on afterwards, but I think you deserve a break. And I think I also deserve a break.